Hello, this is Muskan Singh and my topic is motion on plane curve central orbit with application of Kepler's laws. Let us suppose the position of a particle on the curve at any time t be pxy with arc length from fixed point p1. Let v be the velocity at p and x and y are the components of forces acting on the particle along coordinate axis. On resolving the forces along the tangent at p, the motion is given by mv dv by ds is equal to x cos phi plus y sin phi, where a is equals to dv upon dt into ds upon dt, which is equal to v dv upon ds. Here, as we studied earlier, cos phi is equal to dx upon ds and sin phi is equal to dy upon ds. So the first equation will equals to mv dv by ds is equal to x dx upon ds plus y dy upon ds. Integrating with respect to s, we get mv dv by ds into ds is equals to integration of x dx upon ds plus y dy upon ds into ds plus c1. On integrating, we get mv square upon 2 is equal to phi xy plus c1, and it is known as equation 3, where phi xy is known as work function and half mv square given the kinetic energy of the particle at px. Let initially the particle of mass m starts the motion with velocity v0 from the point p x0 y0. Then equation third becomes half m v0 square is equal to phi x0 y0 plus c1. c1 is equals to half m v0 square minus phi x0 y0. So again equation third becomes half mv square is equals to phi xy plus c1. Half mv square is equals to phi xy minus phi x0 y0 plus half m v0 square. On solving it, half m v square minus v0 square is equals to phi xy minus phi x0 v0 y0. This equation is known as fifth. Now the RHS shows the work done in moving the particle from p0 x0 y0 to p1 xy, where the LHS shows the kinetic energy of the particle. From equation 5, we can say that change in kinetic energy is equal to work done by total external forces. Central orbit. Its definition is if a particle moves under an action of central force, the part described by the force is called the central orbit. It can be circular, elliptical, parabolic, and hyperbolic, etc. Differential equation of central orbit polar form. Let m be the mass of the particle and r, theta be its position at time t. Since the acceleration f of the particle is always directed towards O, the particle has only radial acceleration towards O of magnitude f and no transverse acceleration. Equation of motion along radial direction is given by m d square upon dt square minus r d theta upon dt ka whole square is equals to minus mf. On solving it, we get d square upon r into dt square minus r d theta upon dt ka whole square is equals to minus f. This equation is known as first equation of motion along transverse direction is given by m into 1 upon r d by dt of r square d theta upon dt is equals to 0 d by dt. Now we get d by dt into r square upon d theta upon dt is equals to 0. R square d theta upon dt is equals to h, which is a constant here. Now let r is equals to 1 upon u. Then dr by dt is equals to minus 1 upon mu square into du upon dt. And on solving it, we get minus 1 upon u square is equals to du into d theta upon dt. Minus r square is equals to du upon d theta into dt. Then we get minus h into du upon d theta. This equation is known as fourth. Now d square r into d upon dt square is equals to minus h d square u upon d theta square is into d theta upon dt is equals to minus h d square u upon d theta square into h upon r square. Here 1 upon r is equal 1 upon u is equals to r, so we displace it by r and we get d square r upon dt square is equals to minus h square into u square into d square u upon d theta square. As we know that d theta upon dt is equals to h upon r square, which is equals to h u square. From equation first, d square r upon dt square minus r d theta upon dt whole square is equals to minus f On putting the values from equation A and B, we get minus h square u square d square u upon d theta square minus 1 upon u square h square into u raised to the power 4 is equals to minus f. And on solving the equation further, we get d square u upon d theta square plus u is equals to f upon h square into u square, which is the differential equation of in polar form. Kepler's laws of motion. First law, the law of elliptical orbit. The planet moves in an elliptical orbit around the sun being situated at one of the foci. According to this law, if we consider an ellipse where sun is situated at one of its foci, then the planet is revolving around the sun in that elliptical orbit. And according to the second law, Kepler's second law describes the speed of planet traveling in elliptical orbit. It states that a line between sun and the planet sweeps out equal areas in equal intervals of time. And the third law is the square of the time period of revolution of a planet around the sun is directly proportional to the cube of semi-major axis of the ellipse. The third law is given by t square is directly proportional to a cube. Applications of Kepler's law. As we know that f is equals to u upon r square, and it is also written as mu into u square. The differential equation of central orbit is d square u upon d theta square plus u is equals to f upon h square into u square. D square mu is upon d theta square plus u is equals to mu u square upon h u square. From equation first, we have written this. Then d square u upon d theta square plus u minus mu upon h square is equals to 0. On taking common from both the sides, we get d square upon d theta square u minus mu upon h square plus u minus mu upon h square is equals to 0. D square x upon d theta square plus x is equals to 0. The auxiliary equation of this is d square plus 1 is equals to 0, where d is equals to plus minus I. The complementary function is given by x is equals to c1 cos theta plus c2 sin theta, and we know that x is equals to u minus mu upon h square, so u minus mu upon h square is equal to c1 cos theta minus c2. Now putting the value of u, we get 1 upon r minus mu upon h square is equals to c1 cos theta minus c2. Dividing the above equation by mu upon h square, we get h square upon mu upon r is equals to 1 plus c1 h square upon mu into cos theta minus c2. Comparing this equation with the polar form of equation of conic, which is L upon r is equals to 1 plus e cos theta. Therefore, L is equals to h square upon u and E is equals to c1 h square upon u. The rate of change of sectorial area traced out by the radius vector joining fixed point is constant, since t is equals to area of ellipse upon rate of description of sectorial area pi ab upon h upon 2, and it is equals to 2 pi ab upon h. Now h is written as mu L, where L is the lattice rectum and it is given by b square upon a. On putting its value, we get t is equals to 2 pi a raised to the power 3 by 2 upon root mu. On squaring both the sides, we get t square is equals to 4 pi square a cube upon u into, and on multiplying numerator and denominator by 8, we get t square is equals to 4 pi square 8a cube upon 8 mu. T square is equals to 4 pi square 8a cube is written as 2a whole cube upon 8 mu. Then t square is equals to pi square upon 2u into 2a whole cube, and we can write as t is directly proportional to 2a cube. So this is the proof of the third law of Kepler's